So, the first example that I have in this lecture course is let us look at this functional g of y is integral of x naught to x1 square root of x square plus y square times 1 plus y prime square dx, right. So, j of y is the following quantity. Notice that j depends on all the three variables x, y and y prime, which means if we were to solve for the extremal in Cartesian coordinates, look at the complexity of this Euler-Lagrange equation. So, in Cartesian coordinate we see that this is also equal to d dx of square root, let us just plug in. So, this is my f, and we see that this is also equal to this times this minus y of square root 1 plus y square divided by x square y square is equal to 0, right. So, notice that this Euler-Lagrange equation is a mess. This is extremely difficult to solve. So, this equation is difficult to solve, right. We can still attempt, but there is an easier way out. The easier way out is by the observation that notice that we have the formation of this expression square root of x square plus y square. So, if you recall that in polar coordinate my radius variable r is nothing but x square plus y square, suggests that we should possibly change this functional in polar coordinates r theta or r phi, right. So, what I just said is the presence of square root of x square plus y square suggests using polar coordinates, right, suggests using polar coordinates, or x is equal to x of phi comma r and y is equal to y of phi comma r, right. We know the explicit expression here in polar coordinate x is r cos theta, let us say r cos phi, and y is r sin phi, right. So, what we have is that the Jacobian of x y with respect to r phi is the following, right, it is the determinant of the matrix x r y r x phi y phi, right, and we see that this is also equal to the determinant of cos phi sin phi minus r sin phi r cos phi, right. We see that this is also equal to, after find the determinant comes out to be r, right, and I know that this is not 0 because r is not 0, right. Otherwise the transformation is bogus, it's not a non-singular transformation, right. So, this clearly shows that the determinant is non-singular, and hence we are ready to transform our original functional in Cartesian frame into the polar frame functional, right. Okay. So, then let us further assume, like we assume in Cartesian frame, further suppose that r is a function of I need to make a slight adjustment here. R is my second variable. So, what I will do is I will make r dependent on phi, right. So, r is dependent on phi, right, similar to y dependent on x that we had in the Cartesian frame, right. So, then my y prime, which is dy dx, is also equal to y phi plus y r phi, divided by x phi plus xr r phi, right. And then once we evaluate, we know exactly the relations for y and x in terms of r and phi. So, this is also equal to r cos phi plus r phi sin phi divided by minus r sin phi plus r phi cos phi, right, after just plugging in all the expression for x and y. So which means we also have this term in our functional 1 plus y prime square dx. After doing all the necessary substitution, we will see that this reduces to r square plus r phi square d phi, right. So, now which means, so students are requested to check that this is true for our polar substitution. So, which means our new functional comes out to be k phi r phi is of the form from phi 0 to phi 1. The first term, notice that the first term here is r, right, and the second term is what we had written in the next slide. So, this is r times r square plus r phi square d phi, right. So, we see that this is now completely a function, this is completely a function of r and r phi. This is completely a function of r and r phi. So, we can peacefully use the Beltrami identity, because the explicit dependence on phi is missing in this integrand. So, we are going to use Beltrami identity and reduce, thereby reducing our Euler-Lagrange equation to first order ordinary differential equation. Okay. So, my Beltrami identity this time is in terms of r and r phi, which turns out to be r phi del f del r phi minus f, right. And after plugging in the f, here we have this f. After plugging in this relation, we see that this is also equal to r phi square divided by square root of r square plus r phi square minus r times r square plus r phi square, right. This is also equal to a constant by Beltrami identity. Let us call this as C1, right. So, which means then all we do is simplify this expression that we have written. So, we simplify, we see that the simplified expression becomes r phi, which is equal to r square root C1 square r 4 minus 1, right. So, what we see is the following. We see that phi is equal to the integral of dr by r times square root of C1 square r 4 minus 1, right. Okay. So, we are at a stage now, all we have to do is to integrate this particular quantity, and when we do that, I am going to right away give the answer after the integration. So, we are integrating with respect to phi, doing an indefinite integration. We see that the answer is as follows: phi plus C2 is equal to minus half sine inverse of minus 1 by C1 r square. Okay. So, the extremal is in this form, although it is not clear what is the form of this extremal directly from this expression. So, we do a little bit of simplification, we assume another set of constants. So, let new constants kappa 1 be 1 by C1 and my constant kappa 2 is minus 2 C2, right. So, which means that let me call this as star my star is now given by the following relation kappa 1 by r square is equal to sine negative 2 phi plus C 2, right. Kappa 1 by r square is sine negative 2 phi plus C 2, right. So, this is also equal to, let us just expand this sine of a plus b, this is also equal to negative 2 sine phi cos phi kappa 2 plus 2 cos square phi minus 1 sine kappa 2, right. Okay. So, now let us just multiply throughout by r square, and notice that r sin phi will be y and r cos phi will be x by our coordinate transformation. So, which means in Cartesian frame, in Cartesian coordinates, my extremal is as follows. So, kappa 1 is negative 2 x y kappa 2 minus this quantity can be written as cos square phi minus sin square phi, right. So, this is plus x square minus y square of sin kappa 2, right. So, so that's the extremal that we have found, right, in Cartesian frame. So, notice that we have now found the extremal in the Cartesian frame without ever solving the Euler-Lagrange equation in the Cartesian frame. So, it is via the polar frame that we are able to systematically integrate our equation for the extremal. Okay. So, performing a necessary coordinate transformation helps to simplify the problem, okay, and the choice must be judicious. Okay. So, let us move ahead. So, then the second topic I want to discuss is about the existence of extremal solutions, existence of extremal solutions, existence of the extremal solutions. So, well, just a brief motivation. So far we have just written Euler-Lagrange without even bothering about whether the solution exists or not. We have went ahead and solved the Euler-Lagrange equations in all the examples that we have seen so far. However, we have not worried whether, in fact, even after we are able to solve the Euler-Lagrange, whether the solution makes any sense or not, or whether the constants in the solution, in the family of solutions that we get in Euler-Lagrange, there do exist any constants or not which satisfies the boundary condition, right. So, what I just said is the following: even if the two parameter family of extremals are which are the solutions of my Euler-Lagrange equations can be found, we are able to integrate well, there is no guarantee that the constants C1 and C2 can be found. There is no guarantee that the constant C1 and C2 can be found which satisfies the boundary condition, right. Okay. So, let us look at an example to highlight what I just said. Let us go back to our example for the geodesic on a plane, right. Well, this is my second example of this lecture series. So, let me recall this example of the geodesic integral from 0 0 to 1 1. So, starting at the end point of the square root of 1 plus y prime square dx. So, this is the geodesic problem or the problem of the shortest path, and we know that, as I said, this is the geodesic on plane problem, and we get that the solution is y is equal to x for this problem, which was a unique solution satisfying the boundary condition given by these points on the integral, right. However, let us look at another example which was also done in our previous lecture. Notice this particular case, j given by integral from 0 to pi 0 of y prime square minus k times y square of dx, right. And we know that the solution to this problem was y of x is equal to c1 times cos square root k of x plus c2 times sin square root k of x, right. And we have further seen that the solution is going to exist such that it satisfies the boundary condition, and there would be two cases. If your square root k is not an integer, then y identically 0 is the unique solution that we have, right. And we also saw that if k square root k is an integer, then y is given by c2 of sin square root kx is giving us infinitely many solutions depending on this family of parameters c2, right. So, we have infinitely many solutions described by the parameters c2, right. So, depending on, we see that in this example we could either have a unique solution or infinitely many solutions, right. Now, let us look at another example that we have seen in the past lecture, that is the example of the catenary, right. Okay. So, let us recall the catenary example. So, j of y is integral from x0 to x1 y times 1 plus y prime square dx, right. So, we know that the general extremal of this catenary problem, is y of x is equal to c1 cos hyperbolic x minus c2 by c1. We have just found out the solution to this problem in 2 lectures back, right. And well, let us now further look at a class of this solution. So, without loss of generality, we assume, let us assume our boundary condition x0 to be 0 and x1 to be 1, right. So, in that case my y0 will be c1 times cos hyperbolic of minus c2 by c1, just plug in x0 equal to 0, and similarly y1 is equal to c1 times cos hyperbolic of 1 minus c2 by c1, right. We just plug in the value x equal to 1 here. Okay. So, then the next stage to look at a simplified version of the solution is to change these set of constants, right. So, let us now introduce another set of two constants. So, let me say kappa 1 is c1 and kappa 2 is negative c2 by c1, right. So, in that case my y0 is equal to kappa 1 cos hyperbolic of kappa 2 and y1 is equal to kappa 1 times cos hyperbolic of kappa 1 plus kappa 2, right. So, that is how we get this expression. Okay. Then let us further assume. So, again if we go back to the catenary problem, here we have the coordinate x naught, we have fixed that, we have coordinate x1, fix that as well. Let us also further fix y naught, right, and we are going to describe y1 in terms of y naught, right. So, let us also fix this. So, let us assume y naught is also equal to 1. So, y1 will be described in terms of y naught, right. So, if we do that, we have that y1 is equal to, notice that y1 is kappa 1, but kappa 1 is y naught, well, y naught by cos kappa 2, right. So, this is 1 by cos hyperbolic of kappa 2. So, that is my kappa 1, and cos hyperbolic of kappa 1 plus kappa 2 is cos, well, kappa 1 is nothing but 1 by cos, well, kappa 1 is cos hyperbolic kappa 2. So, I get cos hyperbolic kappa 2 plus kappa 2, right. So, we see that okay, I think this was 1 by kappa 1 in our expression. So, that comes right away from here, right. So, 1 by kappa 1 is cos hyperbolic of kappa 2, that comes from this particular expression here by plugging in y naught equal to 1, right. So, now we have expressed my solution y1 purely as a function of kappa 2, one constant function, right. Now, if we were to plot this function, if we were to plot, let us say we were to plot f of kappa 2 versus kappa 2, right, and I am just showing the solution, an approximate solution from kappa 2 from a range minus 2.5 to 1. This plot has been found using standard softwares. It turns out that this curve has exactly one minima, let us call this as kappa star, right. So, between minus 2.5 to 1, there is just one minima kappa star. So, this question says, this question that we have to ask is there always a solution to this catenary problem? The answer is not necessarily. Look at the case. So, look at case 1. So, suppose you have y1 less than f of kappa star, or let us go back to our let us look at this diagram and draw this diagram, right. So, notice that in this diagram, if my solution falls below this value. So, I have this value here which is f of kappa star. If the solution falls below this value, I see that there will be no solution, right. y1 will not be an extremal to the catenary problem. On the other hand, if I have that y1 is identically equal to f of kappa star, then I have a unique solution to my extremal problem given by the value of kappa star, the constant. On the other hand, if I have y1 greater than f of kappa star, we see that there are two solutions possible. We have two solutions possible, and it turns out that there will be, out of these two solutions, one will be a minima and one will be a maxima, right. So, we do not know which one is minima or maxima, but later on when we introduce the second variation or the sufficient conditions for Euler for the functionals, we will revisit this catenary problem to show that one of the solution is indeed a minima and the other is a maxima, right. So, the conclusion is as follows. So, we conclude the discussion on this topic, and the conclusion we draw is as follows, that even if our analytical solutions of Euler-Lagrange equations, analytical solutions of Euler-Lagrange equations are not available, it turns out that the existence uniqueness, well, the existence uniqueness criteria highlights the existence uniqueness criteria highlights the range of special parameters, highlights the range of special parameters containing regions of either no solutions or unique solution or infinitely many solutions, right. That is what we saw in the above example of the catenary. So, at least we can find regions of the parameter space where we have to search for our solutions to the Euler-Lagrange, right. So, existence uniqueness is also an important issue to consider while looking at the solution to the Euler-Lagrange equation. Okay. So let us